have our second problem here on the DC converters, which are choppers, of course. So on the first problem, on the previous video, we looked at a buck converter. Okay, so if you haven't watched the previous video, please make sure you do so. Okay, now in this video, we're going to focus on the boost converter, and we're going to solve one problem. Okay, so the question reads, okay, the boost converter has parameter Vs equal 20 volts, okay, with the supply voltage. We are given the duty cycle 0.6, the resistance 12.5 ohms, which is of course the load resistance. The inductance is 10 microhenry. We are also given the capacitor, which is 40 microfarad, and the switching frequency is 200 kilohertz. So the first part of the question, you have to determine the output voltage, okay, the average, maximum, and minimum inductor currents, and the output voltage ripple, and then the average current in the diode. Okay, so assuming that it's the ideal component. Okay, so let's get started. So first of all, let me draw the circuit diagram for the boost converter. Okay, so the boost converter here is the circuit diagram. So voltage source, which is DC. Okay, next to it, we connect an inductor. So you have to see the difference between the two, right? Between the buck converter and the boost converter. So I have the inductor here. Okay, and then the position of the switch is here. Okay, so I'm going to make a video and I'll dive into details about how this circuit works. Okay, and then we have a diode. We have a capacitor here. Okay, just to maintain the constant output voltage. Okay, and then we have the load here. So across the load, we get the output voltage. And then this input voltage, we have the inductor here. Okay, so maybe I can just explain a bit about the operation of this circuit. So when the switch is closed, okay, when the switch is closed, you see that what you create here is simply a short circuit. Okay, so I'm going to close the switch. Okay, so when the switch is closed, you create a short circuit here. Okay, so what happens is that if you look at the diode, okay, the diode is more like connected to the negative terminal of the power supply, right? So this node here is at negative potential, as you can see. Okay, so with respect to the diode, this is the anode of the diode, it's a cathode of the diode. If you notice, the cathode of the diode is connected to the positive terminal here of the load, okay, while the anode is connected to the negative terminal, okay, of both the supply and the output voltage. So in this situation, you can say that the diode is in reverse biased. So what will happen is that this will be an open circuit. Okay, so we have an open circuit here when the switch is closed. So this diode forms an open circuit. Okay, so this is what happens. So there's no current going to this part of the circuit, right? Yes. And then, of course, like I said in the other videos, I'm going to derive the equations that are involved. Okay, but for now, I'm just explaining the principal operation of this circuit here. So during the time when the switch is closed, the inductor is going to charge up. Okay, the inductor is going to charge up. It's going to store energy. Okay, remember that an inductor is an energy storage electrical okay, so inductor stores energy, right? Okay, so it's going to store energy during that operation. Next, when the switch is open, okay, so we're going to open the switch. So an inductor is an electrical energy storage element. So we're going to open a switch. Okay, let me bring back the diode. Let's see the behavior of the diode now when I try to open the switch. Okay, so let's see how the diode is going to behave. Okay, so now during this time, you know, the behavior of the inductor is that it opposes, okay, any change. Okay, it opposes any change to the current, right? So what will happen is that that's according to this, of course, the EMF here has to change, of course. Okay, remember that initially it was minus, plus minus here, the inductor was charging, right? But once during the when the circuit, I mean the switch is opened, what is going to happen is that the inductor is going to change the polarity, okay? The inductor will change the polarity, so we're going to have minus plus here, okay? So if you look at this, the diode now is in forward bias, isn't it? Because it's going to the positive terminal, okay, of both the voltage source as well as the inductor. Remember the inductor now this time around is acting like a voltage source. It is charged up, it's storing some charge, so it has voltage across it, right? Okay, so this inductor now and this voltage source, if you look at them, they're in series, isn't it? And both of them are trying to send the current in the same direction, right? So you have positive terminal here, negative terminal here. So this current source is remember the current moves from the positive, from high potential to low potential, right? So to move from the positive terminal, okay? And then this inductor also is behaving the same way, right? Sending current in the same direction. So as a result, these voltages now, they're adding up, they are in the same direction, right? Okay, so they will add up, they will not subtract each other, they're not opposing, okay? So as a result, the output voltage will increase, okay? Because the output voltage will depend on the sum of these two voltages, right? Okay, the source voltage as well as the inductor voltage. Okay, so the output voltage will be high. So that's a basic operation of a boost converter. Okay, that's a basic operation of a boost converter. So this is what is going to happen. The output voltage will be higher, okay, because it will be the sum of the input voltage as well as the voltage of the inductor. Now, what is the formula that relates the input voltage and the output voltage in the boost converter? Okay, so I'm not going to drive that formula, of course. I'll do it in other videos. I'm going to drive it at the moment. I'm just focusing on solving this problem using the same formulas. Okay, so the output voltage. Okay, so the first question we're asked to find the output voltage, right? So the output voltage is given by, okay, the supply voltage divided by 1 minus duty cycle. Okay, so this is a relationship between what? The output voltage and the supply voltage in the boost converter. So as you can see, duty cycle is always less than 1, okay? So this fraction, this part of the, this term will be less than 1, isn't it? The denominator will always be less than 1. And you know that when you divide a number by number less than 1, is the overall, okay? The overall outcome that the whole fraction will increase, right? In short, when you're trying to reduce the denominator, what happens to the whole fraction? The whole fraction goes up. So this voltage here is being multiplied by a number greater than 1, simpler terms, okay? So what will happen is that the voltage will increase. So, and this voltage is also the output voltage depending on what duty cycle, as you can see. So if you're trying to increase the duty cycle, if the duty cycle is very high, right? If the duty cycle goes up, okay? Meaning that the period between on and off is very small. We have a waveform like this, right? So this is a waveform, the waveform, right? Okay, so okay, so this is off period, and then at this point this is T, right? And then you start again, and then it's off during the side, and then 2T at this point, right? Just like that, right? Okay, and then you go, and then this time is off, 3T, okay? So this, the ratio of this, so this time this portion of the waveform is d by t when it's on, okay, duty cycle by time period. And then this one here is 1 minus d by t. Okay, so this is the time period when it's off. This is the off period, right? This is the on period, isn't it? Okay, so what the duty cycle, remember that I said duty cycle is a time when the waveform is on divided by the total time period. That's duty cycle. So you can see that this one is most like 50-50, right? So 50% on, 50% off. Now, what does it mean if you say increasing the duty cycle? It means we are trying to increase the time when the waveform is on, right? That's increasing the duty cycle because look, we're trying to increase the numerator, right? Okay, the period is still the same. We're not changing the period, right? We're trying just to increase the time when the waveform is on, right? Okay, so increase the duty cycle means that we're going to have something like this now, right? Okay, something like this. On period is very big as compared to what? To off period. Okay, so that's the high duty cycle, I mean, right? So this is the period t, and then 2t here, and so on and so forth. So as we're trying to reduce the off period, we are increasing the on period, right? So as a result, we're increasing the duty cycle, right? So it means that the higher the duty cycle, okay, the higher the duty cycle, the higher the output you're going to have, okay? Because if you're trying to increase this number, if you're trying to increase it, what do you have? Oh, okay. It means that you're trying to reduce the whole of this numerator, right? If d goes up, okay, and if d goes down, you're trying to increase the numerator as well as the output voltage also decreases, right? Okay, so you can change the duty cycle by changing the frequency, the switching frequency, right? Okay, by changing the switching frequency, you can change the duty cycle. So in other video, I'm going to derive the equation that relates the frequency, okay, as well as duty cycle and other parameters as well. But in this video, I'll just focus on the solving these problems. Okay, so now let us just substitute the parameters that are given. We are given the source voltage 20 volts. We are given duty cycle to 6. So we can find out, 0.6. We can find the output voltage. So the output voltage will be equal to the source voltage, which is 20, divided by 1 minus 0.6, right? So how much is that? Okay, let me just get my calculator. Okay, so that is 50 volts, right? So that is 50 volts. So as you can see, we curve this. Okay, so the supply voltage was 20 volts, right? But collected the output, which is what? 50 volts. How? Okay, so because that's this connection, okay, this arrangement of the circuit elements, we ended up stepping up the voltage. So these choppers, they behave just like a transformer, right? Okay, transformer, remember that can either step up or step down AC voltage, right? So transformers make use of AC, okay? But choppers, it's DC to DC. Transformer is AC to AC, so you can either step up or step down, right? But choppers, they convert from DC to another DC, okay? All right, so that's the first part of the question, which is part A. And then part B, the average, maximum, and minimum inductor current. Okay, so part B. So I want to find, first of all, I'll come back and do the average, of course, but let me just focus on the I min and I max. So I max is given by, so now this is the what? This is the boost converter. Remember, initially we had looked at what? Or a back converter. How did we calculate I max? Okay, so I max was calculated like this, right? You see, this is the formula that we used for I max and I min. So 1 over R plus 1 minus D 2 LF is the frequency times the output voltage, right? You see, this is for the back converter. Okay, so this one for the back converter, right? Now, let's look at the boost converter. The formulas are different, right? So we're going to have a different formula for this. So the formula is actually given by, so the Imax simply the supply voltage now. We are making use of the supply voltage. Okay, so Vs, okay, 1 over R times 1 minus D squared plus D over 2L times frequency. Okay, so this is for the Imax, right? Even I mean also to be the similar formula on that you're going to have a minus there where there's a plus. So Vs 1 over R 1 minus D squared plus, a minus D over 2L times frequency. Okay, so Imax, so the supply voltage was 20 volts. Okay, 1 over the resistance. Okay, what resistance we're given? The problem here, we are given the resistance of 4.5. Okay, so the resistance is there is 4.5, inductance 10 microhenry, and then capacitance of 40 microfarads. Okay, and the frequency given 20 kilohertz. So I'm just going to substitute those parameters. 4.5, okay, 1 minus 0.6 squared, okay, plus 0.6 divided by 2 times inductance, which is 10 microhenry. So micro times 10 power negative 6, and then the frequency is 200 kilohertz. So 200 times 10 power 3, right? Okay. So if you calculate this, Imax is equal to 13 amps, right? So 13 amps as Imax. Okay. So it's Imax, and then I mean we're going to use that formula. Okay, we use this formula here for I mean. So I mean is equal to Vs is 20, 1 over 12.5, and then 1 minus 0.6 squared minus 0.6 divided by 2 times inductance, which is what? 10 microhenry, okay, times 200 hertz, kilohertz. Okay, and if you calculate that, I mean, is simply equal to 7 amps, right? Okay, and then you can find I average, right? Inductor average current. This is just the sum of these two, I mean, plus I max divided by 2. That's the average inductor current. So 13 plus 7 divided by 2, save what? 10 amps, right? Or we can also use this formula here, very much valid. Okay, so IL average is simply equal to Vs divided by R 1 minus D squared. Okay, so this is equal to Vs, remember that Vs is simply 20 divided by 12.5, 1 minus 0.6 squared, and this still gives you 10 amps. Okay, so still get the same answer, either is the first one or the second one. Okay, and then so we are done with part B. Okay, so A is done. Okay, A is done. B is done. Let's look at C. C says that determine the output voltage ripple. So the output voltage ripple, okay, for the buck converter, sorry, for the boost converter, is given by, okay, C. So output voltage ripple is just equal to output voltage divided by duty cycle, or times duty cycle divided by the resistance capacitor times frequency, or VOD T over RC. Remember that these guys, frequency and period, can interchange, right? Their relationship is begin by 1 over T, or T is equal to 1 over F. Okay, so if you have period, you can use this formula here. If you have frequency, you can use this formula. But in this case, instead of given frequency, then you can use that formula. So the output voltage ripple is simply equal to VO is simply 50, right? Duty cycle is 0.6, okay, divided by 4.5, which is the resistance. The capacitance is 40 microfarads. And then times 200,000 hertz, right? So this gives us about 0.3 volts as ripple voltage. Okay. And then D, we are asked to calculate what are we asked to calculate? So D, we are asked to calculate what the average current in the diode. Okay, so the average current in the diode is same as the current in the load, right? Assuming that there's no current through the capacitor here. So this is ID. So ID is the same as what? IL, right? IR. Okay, let me just name it IR, the current through the load here. Okay, so that one just be the output voltage VO divided by what? The resistance, isn't it? Okay, so this one can just do this. So I average output, okay, is simply the VO divided by the resistance. Okay, so VO is simply 50, given 50 as VO, the resistance 4.5, and this gives us 4 amps. Or there is also another formula here, ID average I simply equal to IL average divided by 1 minus duty cycle. Okay, so this IL is the inductance average current, and this one calculated is 10 amps, right? Okay, so ID average of 10 minus 1 minus 0.6, and to get 4 amps. Okay, so this is the end of the question. So in the next question, we're going to look at a back boost converter. Okay, next video, we'll look at a back boost converter. Okay, so thank you so much for watching. Okay, and please don't forget to subscribe and also share with your friends. Okay, and like, of course, you can comment, you can criticize, whatever. Yeah, that really help me. Thank you so much.